Good day, everyone. I'm Maisa Blanco, and I will be discussing design of irrigation canal. So the success of the irrigation system depends on the design of the network canals. So the canals may be excavated through the different types of soil, such as the alluvial and non-alluvial soil. So the design consideration naturally varies according to the types of soils. So we also have design parameters to consider. So the design considerations naturally vary according to the type of soil. So that's the first. And then second is the velocity of the flow in the canal should be critical. And then third is the design of canals, which are known as Kennedy's theory and Lacey's theory, that are based on the characteristic of sediment load in canal water. So for today, I'll be discussing four methods. So we have the first method for the canal design, which is the unlined canal design on non-alluvial soil. So for the non-alluvial soil, again, they are they are stable and nearly impervious. So for the design of canal in this type of soil, the coefficient of rugosity plays an important role, but other factor like the silt factor, they don't have any role at all. So here, the velocity of flow is considered very close to critical velocity. So the mean velocity given by Chesney's expression or Manning's expression is considered for the design of canal in this soil. So the following formula are adopted for the design. So again, the design of the non-alluvial channel is usually done by Manning's formula or the Chesney's equation. So we have first a formula from Chesney's formula to get the mean velocity. So that's V is equals to C square root of R times S, wherein V is the mean velocity in meters per second, C is the Chesney's constant, R is the hydraulic mean depth in meters, and then S is the bed slope of canal. So for getting the Chesney's constant, we have two formulas. So we have the Basin's formula. So Basin's formula is C is equals to 87 over 1 plus K over square root of R, wherein the K is the Basin's constant and then R is the hydraulic mean depth. For the value of K, if it's not given, then it may be assumed as follows. For unlined channel, it's 1.3 to 1.75, and then for line channel, it's 0.45 to 0.85. So that's for Basin's formula. Then second is for Cutter's formula in order to get the Chesney's constancy. So this is the formula from Cutter, wherein N is the coefficient of rugosity, S is the bed slope, and then R is the hydraulic mean depth. So second is from Manning's formula. So to get the mean velocity, we have this formula. V is equals to 1 over N times R raised to the power of 2/3 times S raised to 1/2, wherein V is the velocity of flow in the channel, that's meter per second, N is the Manning's roughness of coefficient, R is the hydraulic radius of channel, and then S is the longitudinal of hydraulic slope of a channel. And then last equation that we have is discharge by the following equation. So we are already familiar. To get the discharge, Q is equals to AV, wherein Q is the discharge in cubic meters per second. A is the cross-sectional area of water in section, that's square meters. V is the mean velocity in meter per second. If the value of N is not given, then it may be assumed as follows. So for unlined channel, N is 0.0225. For line channel, that's 0.333. And other given formulas on a trapezoidal section, so wetted perimeter from the relation, so that's P is equals to AR. And then the cross-sectional area side slope, that's Z is to 1. So this is the formula that we have. And then also for the wetted perimeter P for the trapezoidal section. Okay, so let's have an example. Again, this is for the unlined canal design on non-alluvial soil. So design an irrigation channel in a non-credible material to carry a discharge of 15 cubic meters per second when the maximum permissible velocity is 0.8 meters per second. Assume a bed slope of 1 in 4,000, side slope 1:1, and Manning's n is equals to 0.025. So we have the given value of Q, V, S, then the side slope, and then the Manning's n. So the first step in the design is to determine the cross-sectional area A. So we can get this cross-sectional area from the discharge equation. So we can get the cross-sectional A is equals to Q over V. So that's 15 cubic meters per second over 0.8 meters per second. So that is, that's 18.75 square meters. So second step is to compute the hydraulic radius. Since we have given V and given S, so we can substitute it to get the value of R for the hydraulic radius. So after the substitution, we can have a value for R, which is, so that's 1.42 meters, right? And then the third is to determine the wetted perimeter. So given the formula P is equals to AR, just need to substitute. So 18.75 over 1.42. So the wetted perimeter is 13.2 meters. Now, for the depth and the B, the value of B, so since there is a side slope given, so the section is trapezoidal. We have already an equation for cross-sectional area and wetted perimeter for a trapezoidal section given. So for that formula, just need to substitute the area and then the Z from the side slope. And then also for the wetted perimeter P, we'll just need to substitute the P and the Z as well. So we have two equations. That's 18.75 is equals to D multiplied by B plus 1D. And then also B is equals to 13.2 minus 2.828 times D. So we'll just need to substitute equation 1 into 2 so we can get the values of D and B. So there, we can get the value of D. So that's 1.94, and then B is equals to 7.7 meters. So therefore, for our design, for this unlined canal design on a non-alluvial soil, the depth is 1.94 meters and the bottom width B is equals to 7.7 meters. Okay, so now let's proceed to our second method. So the second method is for unlined canal design on alluvial soil by Kennedy's theory. So after a long investigation, R.G. Kennedy arrived at a theory which states that the silt carried by flowing water in a channel is kept in suspension by the vertical component of eddy current, which is formed over the entire bed width of the channel, and the suspended silt rises up gently towards the surface. So the following assumptions are made in support of this theory. So the eddy current is developed due to roughness of the bed. The quality of suspended silt is proportional to bed width. It is applicable to those channels which are flowing through the bed consisting of sandy silt or same grade silt. It is applicable to those channels which are flowing through the bed consisting of sandy silt or same grade of silt. Now he established the idea of critical velocity, which will make a channel free from silting or scouring. From long observations, he established a relation between the critical velocity and the fully supplied depth as follows. So that's critical velocity is equals to C times D raised to the power of n, wherein the values of C and n were found out as 0.546 and 0.64 respectively. Thus, 0.46 times D raised to the power of 0.64. Again, they realized that the critical velocity was affected by the grade of silt. So, he introduced another factor m, which is known as the critical velocity ratio. So, therefore, we have a final equation for our critical velocity from Kennedy's formula. So, that's 0.546 times m times d raised to the power of 0.64. So these are the formulas from Kennedy's theory. So this is going to be for inline canal design on alluvial soil. So we have the critical velocity and then the mean velocity from Chezy's formula, and then the value of C from Chezy's constant for using Cotter's formula, and then the equation for the discharge. So let's before we move further, for the Kennedy's theory, it gives more relation between V and D. In this theory, Cutter's equation is used for finding the mean velocity. This theory has no equation for the bed slope, and in this theory, the design is based on the trial and error method, wherein our design must have the same, as much as possible, same value for critical velocity and mean velocity. So that's our goal. So this type of examples or method will be a trial and error method. So one of our examples here for this method is design an irrigation channel to carry 50 cubic meters per second of discharge. The channel is to be laid at a slope of 1 in 4,000. The critical velocity ratio for the soil is 1.1. So use Cutter's rugosity coefficient as 0.023. So we have given values for Q, the S, the M, and the N. So the first step is we need to assume the value for the depth, which is D. So first step is to get the critical velocity. So given the formula from Kennedy, critical velocity is equals to 0.546 m times d to the power of 0.64. So just substitute. So we have come up with a critical velocity of 0.942 meters per second. So that's our result for our critical velocity. Second step is to determine the cross-sectional area. So from the discharge equation, we can get the cross-sectional area, which is A is equals to Q over V. The V will be the critical velocity. That's the V that we will be using. So 50 cubic meters per second over 0.942. So for the cross-sectional area, we have, so we have 53.1 square meters. So after that, we need to determine the channel dimension. So assume that we have a side slope, which is 1:1/2, and our Z is equals to 1/2. So given with this cross-sectional section, so we have also the value or the area that we have from the equation earlier for a trapezoidal section. So that's A is equals to D or Y multiplied by B plus CY. So we'll just need to substitute A and the Z, since we have a given value of Z, which is 0.5, and then we can get the value of B there. So B is equals to 25.5 meters. Then after that, we'll get the wetted perimeter P, also with a given equation for a trapezoidal section. So we'll just need to substitute the values of B, and then also the value of D that we have assumed, and then also the value of K. So we have come up of there. So P is equals to 30.03 meters. Now, after we got the cross-sectional area and the wetted perimeter, so we'll proceed to get the hydraulic radius. So given with the formula, R is equals to A over P, so that's 53.1 over 30.03. So our hydraulic radius R will be 1.77 meters. And then after that, we'll need to compute the mean velocity flow, so we can compare the critical velocity and the mean velocity using this design. Again, our goal here is to have the same, as much as possible, same result. So using the Cutter's formula, we'll just need to substitute it. So we'll just need to substitute the given N and the S, the bed slope, and then also the value that we have for r. So there, we have 1.016 meters per second. That's going to be our mean velocity. We're in the mean velocity is greater than the critical velocity. So this is still not a good result. So we have to repeat the computation in order to increase the critical velocity. So we have to increase the depth. So we have to repeat again the procedure from 1 to 5. So let's assume, since we will need to increase, let's assume that the d or y is equals to 3 meters. So given with the formula, to get the critical velocity, we'll just need to substitute the d or the y that we have assumed, which is 3 meters. So we have a velocity, critical velocity of 1.22 meters per second. Again, second step is to get the cross-sectional area. So we have 40.8 square meters, and then the channel dimensions, we have already given equations, and we'll just need to substitute on the formula given for the trapezoidal section. So we can come up with our channel dimensions of B, and then also we can get the value of the wetted perimeter and then the hydraulic radius. So after that, we can compute now the mean velocity. So here we got 1.16 meters per second, wherein it's less than the critical velocity, which is 1.22 meters per second. So hence we have to try again. So we will have another trial, and we'll try to reduce the depth. So now let's assume that the depth is 2.5 meters. So using the Kennedy's equation for the critical velocity, so there we have 1.087 meters per second. Second is to get the cross-sectional area. Then after that, determine the channel dimensions to get the value of P, B, and the hydraulic radius. Okay, so after that, we'll need to compute the mean of velocity flow. So there we have a value of 1.10 meters per second, which is greater than the critical velocity. So we need to try again. Let's try to increase the depth for this. And again, our goal here, as much as possible, will have same value with our mean and the critical velocity. So let's try to use 2.8 meters for the depth. So we'll just need to substitute, get the critical velocity. So we have 1.169, and then the cross-sectional area, the channel dimensions with a given equation. So we'll just need to substitute that and then get the hydraulic radius. And then we'll calculate the mean velocity. So there you go. We are almost near to our critical velocity. So we have 1.162 meters per second. So with this one, I would say that this will be okay. Critical velocity is equals to 1.169 meters per second. So we can equate it to the mean velocity of 1.162 meters per second. So accordingly, the actual mean velocity tallies with the critical velocity. So we will need to use, with this design, we will use a trapezoidal canal cross-section with that 2.8 meters bottom depth, that's B, which is 13.875, or we can round it off to 13.9 meters, and a side slope of 1:1/2. So that's our example for our using the Kennedy's theory. Now let's proceed with our third method. So unline canal design on alluvial soil by Lacey's theory. So in his theory, he states that the silt carried by the flowing water is kept in suspension by the vertical component eddies. So the eddies are generated at all points on the wetted perimeter of the channel section. Again, he assumed the hydraulic mean radius R as the variable factor, and he recognized the importance of silt grade for which introduced a factor which is known as silt factor F. Thus, he deducted the velocity as V is equals to square root of 2F over 5, wherein V is the mean velocity, F is the silt factor, and then R is the hydraulic mean radius in meter. So here are also the given equations that we can use using the Lacey's theory. So we can go, these are the comparison between the Kennedy's and Lacey's theory. So under Kennedy's theory, it states that the silt carried by the flowing water is kept in suspension by the vertical component of eddies which are generated from the bed of the channel. And then Lacey's theory, it states that the silt carried by the flowing water is kept in suspension by the vertical component of eddies which are generated from the entire wetted perimeter of the channel. Then it gives relation between V and D for Kennedy, and then for Lacey it gives relation between V and R, which is the hydraulic radius. And then in this theory, for Kennedy's theory, in this theory, a factor known as critical velocity ratio M is introduced to make the equation applicable to different channels with different silt grades. Now for Lacey's theory, a factor known as silt factor F is introduced to make the equation applicable to different channels with different silt grades. Now for Kennedy's theory, Cutter's equation is used for finding the mean velocity, and for Lacey's theory, it gives an equation for finding the mean velocity. For Kennedy's theory, no equation for bed slope, and like with Lacey, it has equation for bed slope. For Kennedy's theory, it's a trial and error method, and then for Lacey, it doesn't involve any trial and method. So let's have an example for the Lacey's theory given with the equations for this method. So design a channel of or a discharge of 50 cubic meters per second of silt and silt factor of 1:1 using Lacey's theory. So we have given F, we have also given a Q for the discharge. So our first step is to compute the silt factor, so it's already given. And then second step is to compute the mean velocity of flow. So this is the formula under Lacey's theory. So we have the mean velocity equals to 0.869 meters per second. And then after that, compute the cross-sectional area of the channel section, which is A is equals to Q over V. So that's 50 over 0.869. So our cross-sectional area is, 56.3 square meters. Now, to compute the wetted perimeter of the channel section, we have this formula also coming from the Lacey's theory. So P is equals to 4.75 square root of Q. So we have the wetted perimeter for this channel. And then for the hydraulic main depth for R with the Lacey's formula. So we have we can actually have two results for R using the Lacey and the conventional formula. So for Lacey's formula, we have 1.675, and with the conventional formula, we have 1.677 meters. So the two values are very close and may be taken as correct and okay. So now after we have the hydraulic radius, so let's compute the dimension of the channel section. So for a trapezoidal channel, we choose a side slope of 1V is to 1/2 H, thus Z is equals to 1/2. So using the equation for a trapezoidal cross-section for the area and for the wetted perimeter, so we'll just need to substitute the values for the perimeter and for the Z, so we can get two equations from the area and for the wetted perimeter. So there we can get the values or we can substitute first the value of equation 1 to the equation 2. So there we can get like a quadratic equation. So this one, I would recommend you to use a quadratic formula. So because we will have two results in here. So the first result that you can have on your calculator is given as y to 17.43, but this is very large and feasible, and results will get a negative for the value of b. So using a quadratic equation, we can get two different values for y. So we have 1.85 and then the 17.43. So let's try to use the 1.85. So after we substitute it, then we can have a value of b, which is 29.42 meters. And then after we have the value of b, then we can determine the bed slope for a given formula from Ray's theory. So there, our bed slope is S is equals to 1 in 5,470. So therefore, we will use a trapezoidal canal cross section with depth y or d is equals to 1.85 meters. The bottom depth b is 29.42 meters, and then the bed slope is equals to 1 in 5,470. So this is going to be our design of irrigation for a line canal on a non-alluvial soil using the Lazy's theory. So that's our third method. So now let's proceed to our last method, the fourth method. So we are going to design a line canal. So for line canals, we will not be able to use the Lazy's and the Kennedy's theory for this because the section of the canal is rigid. So Manning's equation is used for designing. So the design's considerations are the section should be economical. So cross-sectional area should be maximum with a minimum wetted perimeter. And then the velocity should be maximum so that the cross-sectional area becomes minimum. And then the capacity of line section is not reduced by silting. So the section of line canal, so the following two line sections are generally adopted circular section. So the bed depth, which is the D, that's circular and with its center at the full supply level and the radius equal to full supply depth. So the sides are tangential to the curve. However, the side slope is generally taken as 1:1. So that's going to be for the design for section line canal in a circular section. So these are the design parameters. So with a given side slope, these are the equation that we can use to get the sectional area, wetted perimeter, hydraulic mean depth R, and then the mean velocity, and then the discharge Q. That's for circular. And then for the trapezoidal section, so the horizontal bed is joined to the side slope by a curve of radius equal to full supply depth D. So the side slope is generally kept as 1:1. And also for the design parameters for the trapezoidal section, these are the formulas we can use for different side of slopes. So let's have an example for our fourth method. So the design the most efficient cross section of a line, a trapezoidal canal, to carry a discharge of 15 cubic meters per second when the maximum permissible velocity is 2 meters per second. Assume the side slope is 1:1 and also determine the bed slope for the canal if the Chassis coefficient is equals to 60. So we have the values of Q, the mean velocity, the side slope, and then we have also the Chassis constant C. So first step is to determine the cross-sectional area. So from the given equation, A is equals to Q over V. So 15 over 2, we have 7.5 square meters for the cross-sectional area, and then the hydraulic radius. So that's R is equals to A over P, which we are still unable to get R from it. So since it's gonna be a trapezoidal section of the following, these are the from the given table as well for the design parameters. So we have come up with the cross-sectional area for a trapezoidal section, and then also the wetted perimeter with a given equation. So we'll just need to substitute, and from there we can get the equation to get R, which is R is equals to D times B plus D over B plus 2A to 8D. So for the most efficient trapezoidal section, R is equals to D over 2, which is we will just need to substitute, so we would be able to get a value of D. So there we have already another equation to get the value of B. So we'll just need to substitute that from our equation from the trapezoidal section for the cross-sectional area. So there we will just need to substitute up until we can get the value of D, which is we have come up with 1.628 meters, and then B is equals to 2.976 meters. So after we have the values for the channel dimension, we will proceed with the bed slope as using the Chessy's formula. That's V is equals to C square root of RS, wherein we have values for C. We have value for R as well. So there we can get another value of S, which is 1/900. So therefore, for our trapezoidal canal cross section, we have a depth of D is equals to 3 meters, bottom depth is B is equals to 1.63 meters, and then bed slope S is equals to 1/900. So this is going to be the last method for the design of irrigation or for different types of canals. Here we have already discussed the 4 different methods for the design of irrigation, for methods for canal design. So I hope you guys were able to catch all of the methods and how it will be solved using the formulas given from Chessy's, Manning's, Kennedy, and Lacey's theory. So thank you and have a good day.